Yes, good morning. We are in Math 111. Today we're going to talk about section 5.5, which is entitled GCF factoring, or greatest common factor type factoring. Now we know that we've been doing what I'm about to do for probably a few years in your earlier math courses. Of course, we're going to press that a little bit at this more advanced level. If I ask you to factor this expression 2x plus 4, well, I'm guessing most students know exactly what to do. You identify the greatest common factor of the two terms of this sum, and the GCF of here, of course, is 2. So that means, working my distributive law in reverse, I can factor out a 2 and end up with an equivalent expression 2 times x plus 2. Alright, if I work this factoring process in this direction, going from left to right, I am factoring. Now you can always check your answer in a factoring type question by working the reverse, and of course that's multiplying. If you multiply this expression on the right, 2 times x plus 2, of course I'll end up with the expression that I started with, 2x plus 4. So some say the process of factoring is really the reverse or inverse of multiplication, and we'll go on to another GCF factoring type problem. Let me talk about the word to factor. Now, to factor in a verb sense means to write or rewrite equivalently a sum of terms as a product of factors, hence the word factoring. A factor is an element of a product, where a term is an element of a sum. Alright, you can see that's what we did in our first example. Let's look at another one. If I ask you to factor this expression, 16y squared plus 24y, well, I have to ask myself, what is the greatest common factor of the two terms in this sum? Well, I like to look at the coefficients first. The GCF of 16 and 24, well, let's write it down here. GCF stands for greatest common factor. That means the greatest quantity that is a factor of both coefficients here in this sum. The GCF of the coefficients is, let's see, 8. And of course I can pull out as many powers of y that are common factors to both terms of the sum. So it looks like 1y is common to both. So I can really factor out a GCF of 8y from both terms of this sum. So if I factor out an 8y, what's left inside is going to be 2y plus 3. Again, you can always check your answer. This is the answer for this problem, 8y times 2y plus 3. You can always check your answer by multiplying. If I multiply 8y times 2y, I get 16y squared, and that checks with what I had originally there. And plus 8y times 3 is 24y, and that checks here. Alright, so I don't always insist that you check your answer, at least formally, in each problem, but certainly if you run into difficulty, you might want to check your factored answer by multiplying and see what you got, see if you get what you started with originally. Let's try another one. Factor something a little harder here. 25a cubed b minus 15ab cubed. Alright, I ask myself, what's the GCF of these two terms in this sum or difference? Well, clearly the GCF, the greatest common factor of the coefficients, is 5, is it not? How many powers of a are common to both terms? One factor of a is common to both. How many powers of b are common to both? One power of b is common to both. So the GCF is 5ab, and working my distributive law in reverse, I can factor out a 5ab from this two-term expression on the left. What's left in inside the parentheses, well, if I pull out a 5ab from the first term, I'm left with 5a squared. And if I factor out a 5ab from the second term, I'm left with a minus 3b squared. So this is my final factored answer in this GCF factoring type problem. Let's do something a little harder. Factor. And this one's a little bit more cumbersome. Let's try it. 3x y squared z cubed plus 6x y z cubed plus 3x z squared. Alright, factor means to factor completely. That means take out everything you can with my distributive law and reverse distributive law type factoring. Well, of course, I have to find the greatest common factor of all three terms of this polynomial. Well, I like to look at the coefficients first. What's the GCF of the numerical coefficients? 3, 6, and 3. Well, the greatest quantity that's common to all three of those is 3, right? So I can factor out a 3. How many powers of x are common to all? I've got one power of x, one factor of x common to all three terms. How many powers of y? Well, this last term doesn't have any y's, right? So I can't factor out a y from all three terms. It's not common. How many powers of z are common to all? Well, I think 2 powers of z, or 2 factors of z, are common to all terms of this sum. So my GCF is 3xz squared, so I can factor out a 3xz squared from this trinomial expression, and according to my distributive law, what's going to be left in each of these 3 slots? Well, if from the first term I factor out a 3xz squared, what's left is y squared z, is it not? Plus, if I factor out a 3xz squared from the second term, what's going to be remaining? Well, I'll have a 2 and a y and one factor of z. Alright, what about this third slot? Well, if I factor out a 3xz squared, well, notice this last term is a 3xz squared. So if I factor out everything I see from that slot, I've got to leave what I call an invisible 1 left, so that when I multiply it back, I get what I started with. So don't forget about that 1 in that third slot. That 1 must appear for this factoring to be correct. So that's the final answer, 3xz squared times y squared z plus 2yz plus the invisible 1. Alright, let's try something else. Factor. 9x plus 16. Well, if I look at this expression, I see 9x plus 16. I look at 9 and 16, and they have no common factor. They're what they call relatively prime. No common factor except for a 1, really, and it doesn't make much sense to factor out a 1. That's kind of redundant. I suppose I could factor out a negative 1, but that's kind of redundant also. 9x plus 16, I'm going to call something like this prime. Just like a prime number can't be broken down, a prime polynomial can't be broken down. So this is a prime polynomial, or I would just call it prime. Right? Can't be factored. Cannot be broken down into simpler products of other factors. Alright, let's look at another one. Well, the book gives this type of instruction. Hang on, let me write down what the book might give us. They say factor a negative 1 from the following expression: minus n cubed plus 2n squared minus 8. Alright, often it will benefit us if the lead coefficient of a polynomial that we're working with is positive. All right. So if the lead coefficient starts out to be negative, like it is here, it's a negative n cubed, it often will benefit us if we can change things around a little bit and make it look like a polynomial with a positive lead coefficient. To that end, I can always factor out a negative 1 from any expression basically by changing the signs of all the terms the sum or difference contains. Alright, so I can factor out a minus 1 from this expression just by writing a negative 1 factor outside a set of parentheses and then writing the original polynomial expression with every sign changed, or every sign the opposite. So my final answer here would be minus 1 times n cubed minus 2n squared plus 8. Okay? Let's look at another similar one. The book might give us an instruction like this. They'll say factor the opposite of the GCF. Well, what they're getting at here is they want your GCF to have a negative sign, and you can always play with the signs of the GCFs by adjusting the signs of the polynomial that remains. I'll give you an example here. Minus 6u squared v cubed plus 8u cubed v squared. Alright, well, what's the GCF in this particular problem? Well, if I look at the coefficients, we got a binomial here with coefficients of minus 6 and 8. What's the GCF of the coefficients? Well, the GCFs of minus 6 and 8 is, well, it's, I suppose you could call it 2, but I think they want the GCF here, according to the author, to have a negative sign in front of it. So instead of factoring out a 2, I'll factor out a negative 2, and I can do that pretty easily. How many powers of u are common to both terms of this binomial? I think I've got 2 factors of u are common to both. And how many factors of v are common to both? I've got 2 factors of v that are common to both. Alright, so when they say factor out the opposite of a GCF, they want the GCF to have a negative sign in front of it. So I'll claim the GCF is minus 2u squared v squared times, well, what's left if I factor out a minus 2u squared v squared from this first term, I will have a 3v remaining in that first slot. You can check yourself. Minus 2 times 3 is minus 6. U squared times, well, no other power of u here is u squared, and v squared times v is v cubed. Alright, so that looks good. How about this next slot? Next term, I should say, if I factor out a minus 2 from 8, I'm going to have a negative 4 left. Remember, be careful of your sign here. Negative 4u, right? So inside the parentheses, I'll have the remaining, or what I call the residue factors, of 3v and 4u with the indicated signs. Minus 2 u squared v squared times 3v minus 4u. Right, and of course we could multiply at any time to check, so I'll leave that for you to perhaps work out. I'll say multiply to check, and I'll say if necessary, not always necessary. Okay. Alright. Alright, 2 more I want to look at here, and they're a little bit harder problems given in the homework list. They're kind of in the upper reaches of the homework list. Let me get a fresh screen here. Alright. This is number 98 on your homework list. And kind of nasty looking. Of course, because it's got the much dreaded fractions involved. Now don't panic. Alright. Alright. 3 halves t squared y to the 4th minus 1/2 ty to the fourth minus 5/2 ry cubed. Alright, how are we going to factor this? Well, let's spot the GCF. What is the greatest common factor of this trinomial expression? Well, if I look at the coefficients, 3/2, 1/2, and 3/2, minus 1/2, minus 5/2. Well, what's the greatest common factor, the greatest quantity I can factor out from each of those terms? And of course it's 1/2. I can pull out a 1/2 from each of those three monomial expressions, and I ask then how many powers of t are common to all, and I notice there is no t in my third monomial in the list, so I can't factor out any t's because it's not common to all. How many powers of y are common to all? Well, let's see, I've got at least 3 factors of y in each of the monomials included, so I can factor out those common powers of y. So my GCF, I'm going to claim it's a 1/2 y cubed, so I will pull out that GCF and work my distributive law in reverse to get the remaining or residue factors. If from my first term I factor out a 1/2 y cubed, I'm going to have left a 3t squared y. Okay. Now from my second term, if I factor out a 1/2 y cubed, I'm going to be left with a minus t y. And if you're confused, just multiply these two to make sure you end up what you started with here in the second position. Now my third term, if I factor out a 1/2 y cubed, I'm going to be left with a negative 5r. So this is my final response, my final result for this kind of nasty GCF factoring problem. Alright, one more I want to talk about. This is number 102. I believe, oops, hang on a minute. I believe this is the very last problem in your homework list. If I ask you to factor this expression, I'm asking you to rewrite a sum of terms as a product of factors. And to that end, we will look for a GCF. Well, again, I'll look at the coefficients first. What's the GCF of 2 and 4 and 6 and 8? Well, what's the greatest quantity that's common to all of those coefficients? That's a common factor of all 4 of those coefficients. Of course, it's 2. 2 is the GCF of the coefficients. Now look at the powers of A. How many powers of A are common to all 4 terms? Well, a to the 4th power is the highest power of A that's common to all 4 terms. So I can take out my greatest common factor by working my distributive law in reverse. Alright, if I look at this first term in the polynomial, if I factor out a 2a to the 4th, I'm going to have nothing but an invisible 1 left, so I write it down when that's the only thing that's left. If in the second term I've got a 4a to the 8th, I factor out a 2a to the 4th, I'm going to have a 2a to the 4th left in that second slot. How about the third monomial here? If I factor out a 2a to the 4th, I'm going to have a 3a to the 8th remaining in that slot. And if I look at this fourth slot, if I factor out a 2a to the 4th, I'm going to have a 4 times a to the 12th power. Again, if you're at all queasy about your final answer, you can always check your answer by multiplying to get to get back and see if you checks with what you started with originally. Alright, we're approaching the 20-minute point, so I'll call it a day for section 5.5, and this concludes the section 5.5 online lecture.